Alright, hey guys. We're going to start back on where we were on Friday with kinetic and potential energy, just to do a little bit of a couple of recaps on KE and PE. You will notice that I'm going to start writing kinetic as KE and potential as PE just for shorthand because I don't really have that much space on my little bit of board right here. So you're going to have to bear with me until I can get a bigger space. So anyway, let's get started. So, um, basically what this slide is saying is we need to remember that um, there are two basic things that we kind of calculate when we're talking about science, and that can be like actual or theoretical yields. We'll get more into that in the chemistry unit next semester, but for the most part, you just need to understand that we do not live in a vacuum, meaning that something that is actual versus theoretical. So when I'm talking about something that actually happened, I'm talking about the real world. So if you get any questions that ask you like, oh, we went to a roller skating park outside at Six Flags, we're talking about something that actually happened because that example is coming from the real world, right? Real world. Okay, now theoretical, on the other hand, that one is going to be basically what the math is telling us. So I'm going to put math right here. So mathematically, what should happen, or theoretically, what should happen. So, for example, if we're looking back at our roller coaster, so I'm going to go ahead and draw a little roller coaster here. This is my idea of a Goliath. If we're talking about our little roller coaster here, right? Theoretically speaking, because we know that KE, or our kinetic energy, is equal to our potential energy, that means that if it is 100 joules at the very top of the roller coaster, when it has the most amount of potential energy, at the lowest point of the roller coaster right here, where we have the greatest amount of kinetic energy, that means theoretically it should be another 100 joules of energy at this lowest point. But we don't live in a vacuum, which means that energy actually is going to transform from one type of energy to the next. So on the way down from the roller coaster, from here down to here, we do have an energy transformation that takes form. We end up getting our potential energy being turned into, some of it is turning into kinetic energy, but some of it is also being turned into thermal energy. Okay? The thermal energy is coming from friction. Excuse my really bad handwriting. The thermal energy is coming from friction. Friction, if you notice, like if any of you guys skateboard or if you ride like roller skates or anything like that, you'll notice that after you go outside for a while and you keep rolling on your roller blades, that if you touch the bottom of it, it's a little hot. That's because the energy is being transformed from one type of energy to the next type of energy. But along the way, we have this magical word here, friction. Friction right here is what is actually turning some of that energy into thermal energy. So just keep that in mind, that sometimes energy transformations can have more than one occurrence. Okay, so now let's talk about a pendulum, because we're going to get a lot of questions that are going to ask you about a pendulum. So, if I have a pendulum, right, and it is going to swing, go ahead and have my pendulum here, and I have a point here, you have another point here, one that goes straight down, which I'm really not an artist, so I'm struggling a little bit here. Just give me a break. You know, a point here, and we have a point here, right? All these are just different points on its road to finishing swinging, you know? So we'll call this point A, and we'll call this A, B, C, D, E. We'll call this point E, okay? I should have just gone ahead and labeled all of them to make my life easier. But anywho, all right, so here is our pendulum swing. So at the highest point on the pendulum, right here, we have the highest, most amount of potential energy. So we're pretending that we're holding something right here and we haven't let it go yet. So if we're just holding it right here, this has the most potential energy, right? So this, I'm going to say max potential energy, right? Okay, now out of all of these here, which one do you think will be our max kinetic energy? Well, our max kinetic energy is going to be on the lowest point. So this point right down here, C, is going to be our max in our kinetic energy. Okay, and along the way, we have, you know, from here to here, we have potential energy decreasing as we have kinetic energy increasing. Okay, which means from here to here, we have kinetic energy decreasing and our potential energy increasing. And then we're back here with some potential energy. Now, do we have max potential energy here? No, we don't. We don't have max potential energy because it is still going to be lower than what we initially started off with. You'll swing here, you'll get a little bit lower. Then our next one would be like here, and then it'll get a little bit lower, and then we'll have here a little lower until we all meet back in the center. You all played with like yo-yos and little things like that when you swing things back and forth. And you just kind of see that eventually it does settle back to the center point. That's what we're talking about. But just understand here that this thing continues to go back and forth. So max PE here. The PE is turning into KE. We have max KE here. KE starts to decrease. PE is increasing. We're going back to the top level of what our PE can be, and then it goes back to decreasing, back to where it was for the max KE, back to going back to this, going to maximum PE and then low level KE, and it does this back and forth, right? So you just really need to remember that you're going to get most of your potential energy from your two ends, and then you're going to have your max kinetic energy down here at the bottom. So where in the pendulum would there be the least amount of potential energy? Remember, I'm not going to answer this question for you because you have to answer it in your Nearpod, but just keep in mind the pendulum, right? You have to keep in mind which one, if they're inversely related, which one as one goes up, the other goes down. So check and make sure. Little hint for you. Here's another one, very similar to the pendulum I just showed you. Like if you were dribbling a basketball, the ball going up, and then it's going to gain its most amount of potential energy at the very top, and then the ball speeds down, going a little bit faster, and then again, down here, we're going to have our max kinetic energy. So just keep in mind that just because the point at the top does not mean that it's kinetic energy. You're looking for your lowest point. You're looking for your fastest point. When the ball is traveling up, it's slowing down, and then it's speeding up as it's coming back down. Your highest point is your max potential energy. Your highest point is max potential energy. Your low point is going to be your max kinetic energy. All right, so kinetic and potential energy have different forms, and we have mechanical, radiant, sound, chemical, electrical, and nuclear, and thermal, which you can't see on this screen, but there is thermal. And how we remember that is by calling it Mrs. Scent, right? So a little mnemonic device that we have, like I said, is that Mrs. Scent. So if I were you, I would definitely write that down. It's really important. It's going to help you kind of remember all the different forms of energy that things can kind of transform into. All right, so the last one that wasn't actually on that one is going to be our thermal or our heat energy. So thermal or heat energy is typically produced by friction, right? So remember I was telling you is that if I'm moving forward, something's pushing backwards, that pushing against my initial like movement is going to be your friction. All right, and friction is what will produce your heat energy. Okay, so friction is moving against something, and then it's going to create your heat energy. But you also can remember that heat energy can cause changes of temperature and change in any form of matter. So it doesn't just have to be like your wheels on concrete. The next one we're going to look at is chemical energy. So chemical energy means that you actually have to break down the bonds of something, right? So if something usually says, I ate an apple and then I ran track, right? That would be an example of chemical energy because your body, you, don't judge my art, you ate an apple, and then your body broke that down chemically into glucose or into carbs or whatever. It's breaking down to a lot of things in your body, kind of helping you out a little bit. And that's what's giving you that energy to run. And then this is my idea of running. running guy. Okay, so that's what's giving you the energy to run. Another example that you would see would be like if I have wood, like a log in fire or something like that. And then we have, fire. And when this gets set on fire, so we'll add fire, and we end up with a pile of ashes, right? That pile of ashes has been chemically transformed from a log of wood to ashes. So that will be a chemical change, and that's what's breaking a bond and creating and releasing energy. This, for example, would be releasing heat energy. So as the bonds are breaking, it's releasing heat energy, and that's how we get warm in the winter with our little fireplaces. The next one we're going to look at is electric energy, and this is probably one you're most comfortable with. It's one when there's a power line that's going to carry something, right? So most of the time it'll be a question that's like, I turned a fan on. What does turning a fan on create? Well, if it's coming from a power outlet, you can be mostly sure that it's going to be electric energy. So for example, again with the fan, it would be electric energy turning into mechanical energy because the electric energy is coming from the power, which is turning on your fan, allowing it to move, which is that kinetic energy, which again is what we've already called mechanical energy. I'll write that down again just so that we can kind of remember. Mechanical energy, I'm going to write ME because I don't feel like writing all those words. So mechanical energy is kinetic energy and potential energy. That was confusing. Let me write it better this way. Mechanical energy has kinetic and potential. That's better. That makes more sense. Let's do that one. Sorry about this glare that I have over here. I hope you can still read it. Yeah, I made it worse. Okay. All right, and then we have electromagnetic energy. We'll cover a lot about electromagnetic energy in Unit 3, but for the most part, electromagnetic energy is going to be your radiant or light energy. This is what I would focus on mostly for now. When questions are typically going to ask you about electromagnetic energy, they're going to refer back to calling it a radiant or a light. But they're going to be like, the sun is producing what type of energy? And you'd be like, oh, electromagnetic energy, or like radiant or light energy. Some questions do kind of switch between electromagnetic radiant or light. It's all under the same umbrella of electromagnetic energy. But it's just that it has X-rays, radio waves. Just think of a whole bunch of different waves when you're thinking about electromagnetic energy for now. And then we have nuclear energy. We don't really go too far into nuclear energy. You just need to understand that nuclear energy does come from the splitting or the fusing of another atom. So if an atom splits or if we fuse an atom together, that creates our nuclear energy, which typically the only time you'd see a question like that is if we're asking you specifically about like a nuclear power plant. There aren't really a whole lot of other examples of nuclear energy. They can be really extra and talk about the sun producing nuclear energy, but for the most part, we're really going to say something around the lines of, if a nuclear power plant was creating, I don't know, energy to power your home, then that would be nuclear energy turning into electrical energy because, you have to have the electric sockets in your house, turning into whatever it's trying to, give energy to in the house. Yeah, so like I said, the sun will give you the nuclear energy, but we don't really talk too much about that, so I don't want you to panic. All right, we're back to mechanical energy, work. So when we talk about mechanical energy, we're talking about kinetic energy or potential energy, just like this picture that I have right here for you. It's pretty much that entire little PowerPoint slide is saying, yeah, mechanics, we have potential, and kinetic is mechanical, creates mechanical energy. So if there's anything that you're like, I don't know if a ball falls from a cliff, I don't know what that is, that's mechanical energy because it's your potential, and it's kinetic because it's going to be falling. So keep that in mind. All right, now we're going to talk about open and closed systems. So this is very similar to what I was talking about earlier when I mentioned actual versus theoretical. So when you have an open system, I'm going to write that down. An open system just means that there's the possibility of energy and matter to escape. So this means typically that you are in the real world. So a real world scenario again would be an open system because we have to take into account that there's air outside, there's friction, there's different things that could come in and kind of mess with what we originally thought was going to happen. And then remember how I talked about theoretical being like math and how we kind of explain it that way? That would be like our closed system. So we have a closed system would be sort of like a vacuum. I can never spell vacuum well. I think it's one C. But a closed system it means that you're basically living in a vacuum. You're living like in space. You're living in this theoretical world where all energy and matter is remaining within the system. So if I'm talking about a roller coaster in an open system, then that means I do have to count friction because friction exists in the real world. But if I'm talking about a roller coaster in a closed system, then that means that the same amount of potential energy that's in is going to be the same amount of kinetic energy that's out. There is no friction. We're talking about a theoretical world. We're only talking about this world only exists in our science minds, okay? When we talk about open systems, we have to include real world information. Make sure you have this in your notes. This is very, very, very important. A lot of questions will ask you about open and closed systems. All right. Sorry, that's my dog. All right, so we have energies conversions. Pretty much that's the exact same thing we've been talking about. An energy conversion just means that we're converting energy from one form to another form. So for example, in a hairdryer, we have electrical energy because it's coming from a socket, which is turning into kinetic energy, as it has little motors that are moving in the back, which in turn creates thermal energy, which is the heat that comes from the blow dryer. So we're going to work on some of these. All right. And if we are talking about a battery, anytime you see anything about a battery, just go ahead and accept that it's chemical. Chemical energy happens in a battery. Also, the same thing, people, if you ever hear like a man rode a bike and he created so and so, like if you hear about a person, it's going to automatically be chemical. If you hear about a battery, it's automatically going to be chemical. These are the little words of wisdom. I'm just going to spec in there here and there. Keep those two in mind, okay? So if I'm going to say, what is the energy conversion for, or the energy transformation for a battery powered alarm clock? Well, I said it was battery powered, so we already know it's going to start off as chemical, right? We have a battery put in the back of the alarm clock. The electrical piece is going to be like that piece down here that's actually taking the energy from the battery and is turning it into electrical energy so that it's able to power our light, thermal, and sound. So if you notice, the light energy is going to be, the colors that we see here that is coming out in the light. Thermal, we are going to have thermal energy a lot of times when you have electrical as well. It's because a lot of the energy, if you touch like right above an alarm clock that you have on for a while, you will feel a little bit of heat, and that is that thermal energy. And then sound energy is coming out when the alarm clock goes off. All right, again, we have a blender. So if it's plugged in, we're automatically going to say it's electrical. If it says it's a battery, we're automatically going to say it's chemical. But in this case, for a blender, it's going to be electrical because it's plugged in, which is going to give us kinetic because, we have those gears that are moving, which is part of that mechanical. The thermal, again, it still gets a little hot when you touch it, and then sound, because we all know blenders get very, very loud. And these are just a couple more. So we have a light bulb, electrical to giving us light and thermal. And these are questions for you to answer. And then there's just a few more examples towards the end here that has energy transformations in an automobile. So we're going to talk about fuel. Again, fuel is going to be chemical because you have to burn it. You have to change the physical properties of it. And then the heat is being changed, into mechanical energy, which is what helps your car move. And more examples here. I think these are all just examples towards the end. Oh, now, law of conservation of energy. I will tell you this once, and then I need you guys to watch the video that I'm going to post as your task, as the task assignment right after this one. That's going to be that cringy science video that helps you remember this forever and ever and ever. And I promise I will ask you this 1,000 times, but after you see this video, I promise you it'll be stuck in your head. I don't know for sure if you're going to be seeing it. You know what? I think you're going to actually already see it at this point, but if you want to watch it again because you weren't here at my Zoom session when I'm going to be playing the cringy science video that we love so much. But the law of conservation of energy states that energy cannot be created nor destroyed. It can only be transformed. Okay, so keep that in the back of your mind. This will come up all year long, all year. So if you had to memorize anything right now, it's going to be this one little quote. Energy cannot be created nor destroyed. It can only be transformed. Okay? And you have one more question that you guys get to answer. But that is pretty much it for today. That is it for your Nearpod. Just make sure that you're getting everything completed. Don't forget to check the tasks and make sure you're completing all your tasks for the day. I saw a couple of you guys were struggling to finish all the assignments, to finish your Nearpod notes. So hopefully this will help you out a little bit so that you don't have to necessarily go through the notes by yourself. You can just kind of listen to me talk through the notes. All right, so I'll see you guys later in our Zoom sessions.